Let's take a look now at the idea of doing some categorical data analysis. Specifically, I'm going to look at the chi-squared test, and we will look at the chi-squared test for the goodness of fit, and we'll look at it for tests of independence. But first, we'll concentrate on the idea of goodness of fit. Now, so far, we've been looking at interval and ratio data, but almost all of our analysis has been based on. This will allow us to actually work with categorical data. The learning objectives. First of all, I want to identify and understand applications using count data. It's categorical data, count data, categorical data. How many observations were there in each of these categories? We want to use the chi-squared distribution to compare two distributions, and use the chi-squared distribution to determine if a relationship exists between two qualitative variables. All right, the data types, I can use this for nominal data or ordinal. I can also use it for interval and ratio data if I create categories and convert that data into count data. Perhaps I'm looking at weights of people. I actually have their physical weights written down, and I'm going to break it down into slender, average, athletic, chunky, something like that. And then based on where I make the dividing lines in my ratio data, I just count how many fall into each of those, and then I've converted that ratio data into ordinal data. So I could use it if I converted the data on interval or ratio data. Now, the data consists of count data, meaning data values represent the number of times a specific category was observed. The goodness of fit test will help us decide if the observed data, what we actually saw happen, fits some type of believed distribution. This is based on what's known as multinomial experiments. Now, look back. Let's go back a bit and talk about one sample t-test. We took a one sample t, then moved that on to a two sample t, so two independent groups, and then went to ANOVA, which gave us multiple groups, right? Okay, when we talked about nominal data, we first looked at the binomial, successes or failures, right? That's not ordinal, it's a nominal. Then we moved to two groups. Well, the binomial first could also be looked at as proportions, right? Then we move to two groups. You have difference of proportions, or comparing proportions from two different groups, although that's still it's nominal data. And now this chi-squared goodness of fit takes that idea and expands it out to three or more. So in a way, it's kind of following the logic from one sample t to two sample t to ANOVA. The binomial, which you can look at in terms of proportions, the binomial to two different groups to now multiple groups, this chi-squared goodness of fit. A multinomial experiment is any experiment which satisfies the following. The experiment consists of n identical and independent trials. Well, that sounds just like we did in the binomial. There were n independent identical trials. Now, the outcome of each trial is classified into one and only one of k different categories. That's what we did with the binomial, except for in a binomial, k was always 2. Now, for multinomial, k can be 3 or more. But it's still the same idea as the binomial. It's just expanded out into multiple groups. The data consists of count data, which is the number of observations, or you can think of this as successes in each of the k categories. A success in category 1 would be that category is observed. A success in category 2 would be that category is observed. A success in category 3 would be that category was observed, and so forth. Where in a binomial, it was a success in one category, or it was in the other category, and we call that a success or a failure. It's taking that exact same idea and just expanding it out to more categories. Now, the probability associated with the k outcomes, denoted by pi 1, pi 2 out to pi k, remain constant for all trials. Gosh, that sounds familiar. What do we say about the binomial? That pi, the probability of success, remained constant from all trials. Well, if pi was success, or pi, the probability of success, was constant, then 1 minus pi, the probability of failure, was also constant. So one forced the other. Well, here, because I have 3 or more, one won't force the others. So I need each group to be constant throughout each trial. What this means is the sum I equals 1 to k of all these individual pi's, pi i's, will be equal to 1. This is the same thing that we saw in the binomial. If I take the probability of success, that's category 1, add it to the probability of failure, that's category 2, it was 1. So now I'm going to expand this out to multiple categories. So if I add up each probability from each category, it will again, of course, sum to 1. Now, the properties of the chi-square distribution are and the basis for this test statistic. The distribution is actually a family of distributions. We've seen this idea before, determined by the degrees of freedom. We've seen this idea before. The curve actually changes. Just like, remember the F distribution, that curve changed depending on the degrees of freedom. The T distribution, remember that curve changed depending on the degrees of freedom. Now, the degrees of freedom for chi-squared goodness of fit will actually be k minus 1. If I have k categories, say 5, then the degrees of freedom would be 4, k minus 1. It's not n minus 1. These k categories, with k is 5, could have 30, 40, 50, 100, 5,000 actual observations, which means n would be as many as like 5,000 or more, who knows. But there's only 5 categories. So it's k minus 1, 5 minus 1, it would be 4 degrees of freedom. Now the distribution is non-negative. It's non-negative, is similar to the F distribution. Now the actual chi-squared, to calculate it, is equal to the sum I equals 1 to n, not k, n, the number of observations, of, I'm sorry, k. I said that backwards. It is 1 to k of the OI minus EI, quantity squared, divided by EI, where EI is the expected value. Say expected number of observations in category I, and OI is the observed number of observations in category I. Okay, so the basis here, the idea behind this is I'm going to take what actually was observed and I'm going to calculate what would be expected based on these pi i's, these probabilities of being in there. Well, think of it this way. If in category 1, the probability of being in category 1 was 0.25 and I had 100 observations, then 25% of those 100 is what's expected to be in that first category. So I'd expect 25. So I take a look at my observed value, what I actually saw happen when I run this experiment, subtract it from the expected value, that gives me a distance. If the observed and expected are the same, that gives me 0, which means it matched perfectly for that category. Well, if you look at this equation here, if all the categories observed matched exactly the expected, this would be the sum of zeros, which would be 0. So, if my observed and my expected start to depart, when I subtract them, that would be the difference. Squaring it keeps it positive, and then I'm kind of standardizing by dividing by the expected value. Now, let's take a look quickly at the, let me see here, I'm going to add a new slide to this. What this means in terms of the test statistic and the distribution. Chi-squared is a positive distribution. It's skewed right. It has similar in some ways to the F distribution. Well, here's 0. When I look at 0, I look at the area under the curve, that's all of it. This will give me a p-value equal to 1. Well, when would you ever reject a null hypothesis with a p-value equal to 1? That's saying there's a 100% chance you just did the wrong thing. But look what happens as the value of chi-squared starts to get big. As the value of chi-squared starts to increase, perhaps it's out here someplace, my test statistic, now this is my p-value, which is clearly much smaller. Well, how does this value get big? If the observed values differ from the expected. If the observed values were exactly equal to the expected, I would have the entire curve. small deviations, and we expect that because of randomness. You wouldn't truly think that you're going to take a random sample and it's going to match some hypothetical or some theoretical distribution exactly. If it did, I'd suspect that you doctored the data. It just doesn't happen. I know there's going to be some randomness, but if the randomness is small, then I'm going to have a very small value for chi-squared, which is associated with a big p-value. If I have a lot of deviations, they're big, they're relatively big, when I calculate chi-squared, this chi-squared value will be big. That big chi-squared value means I'm going to have a small p-value. So large chi-squared is associated with small p-value. A small chi-squared is associated with a big p-value. All right, let's take a look at an example here. You may want to go ahead and enter this data in your calculator so we can work with it. I put the observed values in L1, and I put these pi i's in L2. So you may want to pause the presentation and do that, and then you can match what I'm doing, basically keystroke by keystroke. Now, what is this about? A random sample of students on a community college campus was selected as part of a survey process. Those conducting the survey wanted to determine if the sample was representative of the various ethnicities on campus. This is a very common use for this type of analysis. Based on published data, the true proportion of each ethnicity was obtained. Registration information. Does it seem reasonable to believe the sample was ethnically representative of the campus? All right, so in their sample, they're saying they had 53 people that identified themselves as Caucasian of whites, 27 identified themselves as African American, 42 as Hispanic, 18 as Asian, 21 identified themselves as Pacific Islanders, and then there were 9 that they grouped into this other group. That individually it's too small, so they collapsed them into one group called other. Now, according to data published by the campus, 35% of this particular campus is white, 12% were African American, 31% were Hispanic, 5% Asian, 13% Pacific Islander, and 4% other. And the question is, these observed values, how well do they match these proportions? Do they match it well, or is there an issue? Did one ethnic group get underrepresented, which means others must have been over? Or likewise, did one get highly overrepresented, which means some of the others must be under? Okay, what we need to do is calculate these expected values and look at the null alternative hypothesis. So I'm going to start off with a null alternative hypothesis and then get to the expected values. The null hypothesis is going to be a little bit complicated, not too bad. I hope I have room to write it here. Pi sub w, which is the proportion of whites, is, in fact, 0.35, as it should be. Pi sub, I'm going to use AA for African American, is 0.12, which is the proportion that's reported on campus. Pi sub h for Hispanics is 0.31. Pi sub a for Asian is 0.05. Pi sub p for Pacific Islander is 0.13. And last but not least, pi sub o for other is 0.04. So the null hypothesis is that our proportion in our sample actually matches within reason, within randomness, of what should happen. The alternative hypothesis, very much like an ANOVA, would be at least one of these groups is not equal. Somebody's different. Some group is not proportionately represented. Alpha, I'm going to stay with 0.05. And chi-squared, if I actually did the calculations, I took the O's minus the expected, and this should be squared, divided by expected values. If I summed all that up, then I would get my actual chi-squared test statistic. So I need to calculate these expected values. Now, it's actually pretty simple. All I need to do is add all these up so I know what n is, how many people I have total in my sample. And 35% of them should be white. So 0.35 times n will give me pi 1. So I'm going to say this is n times pi 1. This will be n times pi 2. Well, actually, I suppose I should change this to pi w. Stay with the same notation. Pi AA. This would be n times pi h, n times pi a, n times pi sub p, and n times pi sub o. So let's go to the calculator very quickly here. In L1, I'm going to clear that out. In L1, that's where I put the observed values. L2 is where I put these theoretical or these reported proportions. So all I need to do is add up L1 and find out what it is and multiply by L2. So I'm going to go to Stat, Calc. I'm going to actually use two variable statistics here. You don't have to, but I'm going to check something very quickly all at the same time. And I'm going to do L1 and L2. Hit Enter. And right there, 170. The sum of the x's, that's L1, the first group. So there's 170 people in here total. Now the reason I did two variable statistics is I'm going to come down quickly here and look at the y's. And look at the sum of the y's. There it is. The sum of the y's is 1. Well, it better be. I'm making double sure I didn't have a typo in there and that my proportions is off. When I add up all the proportions, it better be 1. So that was just a quick check to make sure that I'm not setting myself up to be totally messed up before I even started. So I'm going to get out of there and go back to the editor, go up to L3 and say this is 170, that's n, times L2. I'm going to take the total, multiply by each individual proportion, hit Enter, and there are my expected values. So if I jump back to the computer, I know this expected value is 59.5. The next one was 20.4, 52.7, and so forth. I actually already printed them up, so there they are. There's all the expected values. So now if I'm going to calculate this by hand, which I really don't want to do, matter of fact, I'm not. I'm going to let the calculator do it for me. But if I had to do it by hand, I could just take the observed minus the expected value, 53 minus 59.5. I'll do the first one for you so you can see it. 59.5. Whatever that value is, I'm going to square it. Divide it by 59.5. Add it to the next one, which is going to be 27 minus 20.4, square it, divided by 20.4, and so forth. Do it to each of these. That will give me my test statistic. And then I could go into the calculator or use a table. We're not using tables in this course, but or in this book. The calculator will actually has a chi-square distribution in there, and you can calculate the p-value. Rather than that, I'm going to switch back to the calculator. I will go to Program and run the program Good Fit. So if I run it, yes, I am stored in a list. Where's my observed counts? Well, I'll put the observed in L1. Where's my probabilities? I put those guys in L2. And there it is. So I'm going to switch back to the computer, and I know that if I were to actually do this by hand, within rounding, I ended up with a test statistic of 16.4020. But what I'm really interested in is the p-value, which equals 0.0058. This p-value suggests that I should reject the null hypothesis, which is saying that based on ethnicity, we didn't do a very good job of properly representing each group. Now, for this course, we're not going to go into further analytical techniques to figure out where we went wrong, but you can quickly get a good idea simply by calculating what proportion you actually got, and then take a look at which group seems to stick out that, or groups that does not very well match what should have happened, and you get a good idea where things went wrong. Now, you notice that I kind of skipped the assumptions when I did this test. And so let's go back to the assumptions. And there's a reason I skipped it. The assumption number 1, you should do beforehand. The experiment satisfies the properties of the multinomial experiment. Well, it does. In this particular one, I'm looking at ethnicity in the survey. So when I grab somebody, look at their form, I look at what they check. If they check Hispanic, then they go in the Hispanic group. They're not going to go into the Hispanic group and the Pacific Islander. They check one category. It's only going to be into one group. It's independent. If the first person was Hispanic, it tells me nothing about the next person is going to be, and so forth. So if I look at all that stuff within the multinomial, it's clearly satisfied in this particular example. Now, parts 2 and 3, I couldn't do that before I started the analysis because it's about the expected values. Well, part of the analysis was looking at the expected values. All the expected values need to be at least 1. If I have an expected value that's less than 1, it can really balloon. It can really blow up the value of that chi-squared value and give you false readings or false results. We need to make sure all of our expected values are at least 1, and that no more than 20% of the expected values are less than 5. Well, let's jump back. My expected values, they're all 1, or all at least 1, and none of them are less than 5. So my expected values are good to go. Or my assumptions are good to go. There's not a problem with it. Everything looks just fine. So, that's it on the goodness of fit test. I've addressed my assumptions, which I agree is a little bit backwards because I'm going to actually enter the data, do some calculations with it, and then come back and address it, which is not that big of a deal. You could address it all first. Whatever, it's not that big of a deal. In the next example, when we move from goodness of fit to test of independence, the way the calculator actually does the calculations for you, you could do the expected values first, but it's so much easier because the calculator has a built-in capacity or capability of doing the expected values for you. So I would actually check to make sure it meets the assumptions for multinomial, run the whole thing, and then look at the output from the calculator, examine the expected values, and say, yeah, it's fine. But we look at that next when we take a look at the idea of not goodness of fit, but tests of independence.